In this video, we'll discuss correlation testing, or how to statistically test for significance in a correlation coefficient. We'll also discuss how to statistically and practically interpret the results. So correlation testing can be done in comparing the test statistic to another known statistic. Typically, we have null and alternative hypotheses that you've seen before. The null hypothesis typically is rho equal to 0. Now note that rho doesn't have to be equal to 0. Rho can be tested against any particular number, and in the same token, the not equal to sign here could be greater than or less than depending on the test that you're trying to make. The test statistic is given by t and can be written like this. T equals the correlation coefficient divided by the square root of 1 minus the correlation coefficient squared divided by n minus 2. One of the nice things about this formulation of the test statistic is that this test statistic only depends on r, the correlation coefficient, and n, the sample size. Note that this is compared to a t-distribution with n minus 2 degrees of freedom. So as you looked at the t-distribution in your previous classes, this is the same t-distribution. The interesting thing here is just the degrees of freedom is n minus 2. So we'll continue our example. Excuse me. So we're going to copy and paste our equation, and then we're going to fill in the values that we had. So the values that we had in the previous example was 0.795, excuse me, 0.795 squared, and 5 minus 2. Solving for this value, we get 2.270, and again, this would be compared to a t-distribution at a given level of significance, alpha equals 0.05 or whatever alpha level you're using, the t-distribution having n minus 2, or in this case 3 degrees of freedom. The t-distribution with the degrees of freedom equal to 3 and alpha of, let's say, 0.05 for the critical value is 3.18. So when looking at a critical value of 3.18, this is for a two-tailed test, so we compare with positive and negative 3.18. So we're looking to see if this 2.270 value is below negative 3.18 or above positive 3.18. Quickly, we can demonstrate a visual of this. As you've no doubt seen in previous courses, the t-distribution looks very similar to a normal distribution. When we're assessing the cutoffs, what we're determining is the regions of significance at the edge of each of the sides of the t-distribution. Recall that t-distributions change depending on the degrees of freedom, so we have to list the degrees of freedom with each t-distribution. For this t-distribution, our cutoffs are set at negative 3.18 and at positive 3.18. The value that we're seeking to test is, let's check real quick, 2.270. So 2.270 on this graphic would fall roughly here. Looking at our regions of significance on either side of this graph, we see that 2.270 is not in one of the significance regions. It falls in the non-statistically significant region, so we would declare not statistically significant. In R, a test of a correlation can be done using the core test command with lowercase t. So we would give core test two vectors, x and y, and typing this into R, this would give us our t statistic, the test statistic that we had earlier, it would give us our p-value for the comparison, etc. Recall that we never accept the null hypothesis. Our conclusions are only reject the alternative, or excuse me, reject the null, or fail to reject the null. Note that the second one, this is when we get tempted to say we accept the null hypothesis, but again, statistically, we never ever do that. All we do is fail to reject the null hypothesis. With this, let's move on to some example interpretations. For context, and again, interpretations will tend, good ones, will tend to involve the context of the situation. We'll go through some bad ones and good ones. But for context, consider x to be age, so x is our age variable, and y is weight. So we're assessing the linear relationship between age and weight. A test of the correlation coefficient is saying, is the linear relationship between age and weight 0? Or is the linear relationship between age and weight not 0? That's what our hypothesis test is. The test statistic is merely a calculation we use to test these particular statistical hypotheses. And then we have our calculation and our determinations of significance. Now it's important up here to realize exactly what we're testing and to visualize what this would mean. So we're using a non-directional test, which just means that this is not equal to. Recall that we can use greater than or less than to assess a positive relationship or a negative relationship. In this case, we're not sure which one it would be. A negative relationship would imply that as age increases, weight would decrease. Recall that a negative relationship means that as one variable increases, the other decreases. A positive relationship would mean that as age increases, weight increases. Now this is important to realize as you're considering the meaning of these and as you're writing an interpretation, to realize what the possible outcomes could be and what this test means. This test, not indicating a direction, means that we're not indicating whether or not it's a positive relationship. We're simply indicating that the strength is non-zero. So there's a couple of different types of interpretations we can do. This isn't formal, this is just how I classify them. First is a statistics-y interpretation. These are things like, we fail to reject the null hypothesis at the alpha equals 0.05 level. Though this interpretation is technically correct, a layman reading this interpretation, if you gave this to your boss or a client, would not necessarily understand what you're talking about. Note that in this interpretation, we're not talking at all about the context. We're not talking really about the strength of the variables or anything like that. We're just saying that it didn't meet this particular threshold and leaving that information there. Perhaps a slightly better and more standard statistics interpretation. This is very standard, but again, rather dry. Something that would be better, but still more statistics-y than practical, is saying that there isn't enough evidence to determine a linear relationship between age and weight. And again, I'm using age and weight here, but if you're using this in a future example for your own write-up, you're going to want to make sure that you're putting your own variable names in. Now, in this interpretation, it's still important to list the alpha value by which the comparison was done. So if we're saying there isn't enough evidence, well, there may have been enough evidence at a different alpha value, but there wasn't enough evidence at our alpha value. So it's important to list this alpha value because it actually impacts the degree of conclusion that you're making in your write-up. For practical interpretations, these are another style. Note that above, this kind of depends on context. This first one doesn't at all depend on the context. The second one somewhat does. It discusses the variable names at least, but it doesn't actually provide much in the way of interpretation for a client or a boss. For that, we can provide a more practical interpretation. Now, these interpretations, at least as I teach them, tend to deviate somewhat from a very straight arrow interpretation of the statistic. Rather, the goal of these interpretations is to help someone understand what you're trying to say and what the statistic says about the context in which you're studying. One way in which I explain this is to say, pretend you're explaining this concept to your little brother or sister. Pretend you're trying to describe this to a 10-year-old. Someone who can perhaps understand the big picture details, but doesn't understand all of these technical aspects of the statistics that we just calculated. How would you explain this? So maybe one explanation would be something like, as age goes up, it looks like weight doesn't linearly increase. And maybe a graph would be helpful for determining if it increases or decreases non-linearly. If you remember in the last lecture, we did a graphic where we had an increase or decrease using a quadratic function that was clearly indicated in the graphic, but our statistic would have indicated no linear relationship. And actually here I should write increase or decrease, excuse me, because again we made a non-directional hypothesis. Other things that you could include here, and this is very open-ended, but comments or considerations about why this may be the case. Maybe it's the particular sample. Maybe in this sample, individuals were already full-grown adults. So as their age increased, we might expect weight to increase in children, but after you're a fully grown adult, there may not be a relationship between age and weight. So maybe the particular sample had something impactful. Maybe another relationship was observed tentatively, and you can't talk about other relationships unless you statistically test them, but you can mention that this was observed and mention that future statistical testing could discuss it. And there's other things that you could discuss on this. These types of considerations are something that I will expect in your write-ups. Typically, you'll want both. You'll want both a statisticsy interpretation and you'll want a practical interpretation so that you can be technically correct in your interpretation of what the statistic means, but you can also be understandable to a layman in terms of what the statistic implies about the situation that you're studying. So let's write that statisticsy for technically correct and practical, so people actually know what to do. Now you should also consider your audience when you're writing this in real life, and this is one of the reasons why we will do both in this class. Typically when I'm reporting for clients, I also report both virtually every time. There is very rarely a case where I provide a statisticsy interpretation without a practical interpretation. There's occasionally a case where I'll provide a practical interpretation without a statisticsy interpretation, but never in a formal write-up and never in a poster or project. That would just be maybe conversationally. I might mention a practical interpretation without a statisticsy interpretation. But if I were writing it up for someone, I would make sure to include both. But again, your audience, though it may not indicate whether you could exclude one, may indicate whether you should focus on one or the other. So know your audience to know which you should emphasize. And again, in this class, I'm going to want you to provide both so that you can get some practice working on both a statisticsy interpretation, being technically correct, and these are very easy actually, because you almost just copy and paste except for your situation and your conclusion. The practical interpretations you have to think about a little bit more, and again, that's good practice. There's another way in which we can approach sample interpretations, and that is using p-values. So a p-value is a very common way in which these statistics are reported. I know you've seen p-values before. But p-values can be, and frankly often are, used in formal write-ups. Quite frankly, I would never use an alpha value like this. Never do a test. I do tests at the alpha level, but I don't do them using critical values. I do them using p-values. So recall that when looking at a p-value, you compare your p-value to your alpha level. I guess we can write this real quick. If p is less than alpha, then you have significance. If p is greater than alpha, then you have non-significance. So, for example, the above write-up may be rephrased with a p-value. Now notice that we didn't calculate a p-value in our write-up. We would have to use the core.test function to find the p-value. So we could copy this statistics interpretation, and all we would do is we would take this exact style of interpretation and we would replace alpha equals whatever value with p equals whatever value. In this case, the p-value rounded out to 2 decimal places would be 0.11. Quickly, here are a few thoughts on how you can properly include p-values. And again, this is something that many researchers do. This is preferred, but you need to make sure that you're doing it appropriately and avoiding some of the common pitfalls. So first step when you're including p-values is for your entire paper, not just for this section, but for virtually everything in your paper, set an appropriate number of decimal places that you want to go out to. A good default is 2 decimal places. This is the APA default standard. If you have a good reason, you can change this, but make sure you have a good reason to do so. Also remember that even though you're setting this for your whole paper, if you have integer numbers, there's no reason to write every integer as a decimal place. Just put decimal places where the numbers are being calculated out to that decimal. Once you have this, the tip is just to list the p-value at that appropriate number of decimal places. One of the tricks, though, is if p would be listed as 0. If p would be listed as 0, so here I might have p equals 0.00. If that's going to happen, then instead list it as less than the smallest non-zero number. And that sounds complicated. I don't mean it to be complicated. It's actually much easier in practice. For example, if p rounded to p equals 0.00, instead write p less than the smallest number at 2 decimal places. So the smallest number we can write at 2 decimal places is 0.01. The reason for this rule comes because the p-value can never be 0 when we're doing calculations with non-identified data. So if we're doing calculations with data that aren't systematically set from one variable to another, that are independent variables, or variables that are different from each other, then we never ever have p equals 0. What we may have is p is less than the smallest value to which we're going. So that would be 0.01 in this case. Now let's say in your paper you had something, you were going out to 3 decimal places. So for 3 decimals, if p rounded to p equals 0.000, instead we would write p is less than 0.001, which would be the new smallest number that we could have at 3 decimal places. Remember though, never equals 0. So we never, ever, ever want to write this p equals 0. These are bad things that we do not want to do. So maybe we can put a little strike through them because we don't want to do that. Rather, this is how we would write a p-value in a write-up. And again, typically we use p-values in write-ups. So this is how you would be expected to do those write-ups. And again, here, you would write the p-value if possible, but if p is rounded to 0, then you would write something like p is less than 0.01 in this same space. There's an alternate use of p-values that you'll occasionally see in articles. I won't say that I've never done this, but it has recently fallen out of favor. So I would tend not to do it unless I had a good reason to, but it is done. In general, this references the alpha cutoff and describes p in relation to alpha. For example, with alpha equals 0.05, instead of writing p equals 0.11, we would write p is greater than the alpha value. As a rule, we would have either p greater than that alpha value or p less than that alpha value. Now, be very careful here. I'm using 0.05 because that was my alpha value for the problem. If the alpha value for your problem is a different alpha level than 0.05, then you would change this number to represent whatever your alpha is. So say you're working in a problem that has alpha equals 0.10, then you would write either p is greater than 0.10 or p is less than 0.10, depending on what the p-value is. In this case, p would be greater than 0.10 because 0.11 is greater than 0.10. So for an example, let's take this exact same section that we had, copy and paste it, and now instead of having that p-value written out, we have p is greater than that alpha level 0.05. One final and somewhat random topic is on the coefficient of determination. Final topic for today's video anyway. In bivariate correlation, this just means between two variables, so what we've been talking about thus far. And in simple linear regression, which will be an upcoming video soon after we're done with correlation. Pearson's correlation coefficient can be used to directly calculate something called the coefficient of determination. This value, often listed as r squared, and frankly often just called r squared. We very rarely use the term coefficient of determination. You'll hear all the time as we talk about this quantity, people discussing r squared. It represents the amount of variation in one variable that is explained by another. This is a common variable to report in a whole ton of different statistics. The other reason this is common is not just because of how easily it's used, but because it's a very important variable if you consider how much variability in one variable is explained by another. That's kind of like asking how much does one variable connect with another. This is a really cool question that very often we want to answer. To calculate r squared, simply square the correlation coefficient. That is, little r squared equals capital R squared, at least for bivariate correlation. So this gets a little trickier when we have fancier statistics. That is, when we have more than just two variables that we have in bivariate correlation. But the meaning of this statistic will stay the same. That is, this statistic will still represent the amount of variation in the outcome represented by either another variable or another group of variables. This video has demonstrated how to perform statistical hypothesis testing for Pearson's correlation coefficient, as well as how to interpret that hypothesis test, and a brief discussion of the coefficient of determination, or r squared. In the next video, we'll discuss a new type of correlation that can be used in some particularly fun circumstances.